So now today I'm going to talk about the last dipole Vandarwall force, which is in the molecular forces. Instantaneous. Maybe spelling is not right. You can check yourself. Dipole induced dipole interaction, which is also known as London interaction, which is also known as London or dispersion forces. Now, what does it mean? Let's decode it. It means that instantaneous, which means leave it. I'll write it here, so it will be more. It will be fine. Instantaneous means instantaneous, which means for a time interval. For a time interval, two non-polar molecule becomes polar due to induced dipole. One is instantaneous dipole, one other is induced. Let's take an example. For example, I have two hydrogen molecules. This is one hydrogen molecule, H2. This is other hydrogen molecule, H2. For a while, let's make an atom here. For example, this is hydrogen molecule, H2. This is other hydrogen molecule, which is H2. So for a while, what happened? And for an instant time interval, this electron just accumulate here or comes here, and the hydrogen positive ion moves in this side for an instant time interval plus, and here this positive charge attract the electron toward itself, like in this direction, and the positive charge moves here for a time interval. So this is instantaneous dipole, and this is induced dipole, because this instantaneous dipole creates a neighboring atom or induce a dipole movement in the neighboring atom. In this way, this positive attracts this electron toward itself, but this happens only for a very short interval of time, and this interaction for a particular time interval, which is weakest among all the Vanderwall forces. This instantaneous dipole interaction, dipole induced dipole or dispersion or London forces is the weakest among all the Vanderwall forces. So I would like to discuss a very important concept here, which is known as exception. Let's discuss with exceptions here. So the exception is that whenever we talk about the halide of certain metals, we know that we are exceptions. Whenever we talk about the halide of these metals, which is aluminum, beryllium, magnesium, magnesium, or I guess lithium. Yes, lithium. And for example, the halides is something like this. When the chlorine, bromine, and iodine making bond with these aluminum, beryllium, magnesium, and lithium. What chlorine? Okay, let's do chlorine, bromine, iodine. Not iodine. Yes, we can say that iodine is there. And when this chlorine, this is basically, we know that it is non-metal. It is non-metal, and this is metal. And when one non-metal creates a bond with a metal, we can say that yeah, it's ionic in nature. But according to Fezant rule, we know that the ionic compound has covalent nature. In ionic compound, we can encounter a covalent nature. In ionic, covalent nature is there. In ionic compounds, covalent nature can be encountered. Covalent nature. In ionic, we can encounter the covalent. So when this is exception, when this metal creates or makes a bond with these non-metals, it is basically covalent. This is not an ionic bond, this is covalent bond, it is covalent in nature. For example, aluminum chloride and aluminum chloride, magnesium bromide, or magnesium bromide, magnesium bromide, or a lot of examples. Lithium iodide, yeah, I do. A lot of examples are there. Lithium, let's take in space, iodide, lithium iodide. And whenever these metals makes a bond with these non-metals, which are chlorine, bromine, and iodine, so this is basically covalent in nature. And now we can judge the intermolecular forces in them according to their polarity, which means that if we talk about here aluminum, chlorine, for example, let's create an order here. So it will be example easy for you to understand. For example, now I'm creating an order here: magnesium bromide, magnesium chloride, aluminum, magnesium bromide, magnesium bromide, magnesium Br2. Yes, I just forgot to put magnesium. 1 minute. Magnesium iodide, magnesium chloride, magnesium bromide, and magnesium iodide. If we talk about if you can see here, magnesium chloride, magnesium bromide, and magnesium iodide we have here. And if I talk about their molecular weight, so it has a large molecular weight. Then this and this, then this. And if you put this in this order that this is greater than this is greater, it's wrong. When we have such metals making bond with a non-metal like chlorine, bromine, and iodine, and aluminum, beryllium, magnesium, lithium making bond with chlorine, bromine, iodine, we judge it on the basis of their polarity. For example, chlorine is more electronegative, so their order be something like this. First is magnesium chloride, then magnesium bromide, then magnesium iodide. So this is exception here, right? There are 3 certain ways for judging that whether you judging the let's write in the note intermolecular wonderful forces. The first is nature. The first is nature. The first one is nature. And if the nature of the molecule is same, then we talk about their molecular weight, right? And if the higher be the molecular weight of the molecule, the more the boiling point it has. Remember this thing as well. Higher will be the molecular weight, higher boiling point. And when we talk about isomers like N-butane, isobutane, neobutane. Okay, let's see what does it mean. We know that that's when we talk about the isomers, let's take example of butane, isobutane. So let's create a molecule here, isobutane and neobutane, and let's take example of N-pentane. What's the formula? C5H12 N-pentane. We know that it's something like this: CH3, then CH3. Oh my god, it's difficult for me to create it. We're taking a lot of time. Then CH3, in this way 3 carbons, then CH3, then CH, in this way 5 carbon, 1, 2, 3, and then again CH3, right? So this is N-pentane, a straight line, not branched. Then we talk about isopentane. So isopentane is something like this: CH3, CH3, CH, then branch, CH3. Whenever we talk about isomers, we judge it on the basis of their surface area. Then again CH3. This is isobutane. Not isobutane, I'm sorry, I'm consecutively talking about isobutane. I'll be giving example as well. This is so yes. And now I'm going to talk about mu will be something like this: CH3, C, here CH3, here CH3, and here CH3 as well. So which has a large surface area? Of course, and pentane is a large surface area, so it has more van der Waals forces. So when we talk about isomers, we judge it on the basis of surface area. So this was the basic trick that you must know.